Using water to measure the value is useless. It evaporates too quickly. We've been working on this for weeks now and we still haven't found a value.
Just drop it. We've been at this for so long. Let's just enjoy our chicken.
We can use the oil from the chicken.
What is the true nature of an electron's charge? Is it unquantifiable, or is there a specific fundamental unit? Electrons were first discovered by J.J. Thomson in 1897 through his cathode ray tube experiment, which determined the existence of a negative subatomic particle, revolutionizing science. Who knew that tiny bores could have such an impact on the field of physics? Concepts of atoms and electrical charges emerged, yet no scientist had accurately measured the charge of an electron, and whether its value was discrete or continuous was still a topic of hot debate. This uncertainty eventually compelled American physicists Robert A. Millikan and Harvey Fletcher to create the oil drop experiment, occurring in the University of Chicago between 1909 to 1913.
Millikan's oil drop experiment consisted of an atomizer housing oil, an enclosed chamber divided into an upper and lower compartment, parallel plates connected to a power supply, an X-ray, and a microscope, both positioned towards a stream of oil droplets. Millikan began the experiment by dispersing oil droplets into the chamber using an atomizer.
A fine mist of oil is generated through Bernoulli's principle, which states that increasing the speed of a fluid decreases its pressure. When the bulb of the atomizer is squeezed, fast-flowing air blows over the compartment holding oil, creating a low-pressure area, which contrasts the relatively higher pressure of the atmosphere. The difference in pressure and the friction of the fast-moving air breaks the surface tension of the oil, forcing oil particles out into the chamber as a fine mist.
The oil would then fall from the upper to the lower chamber through a tiny hole in the top plate. Using ionizing radiation from the X-ray, electrons from the air particles are essentially kicked out, moving in with the oil droplets. This ionizes the air, causing the droplets to gain a negative charge. Through the microscope, Millikan was able to observe the oil droplets as they fell. However, he observed that each droplet size and the rate at which they fell varied. He then recognized that the core force responsible for dragging down each droplet at the differing rates is its weight force, calculated by mass times gravity.
Alternatively, air resistance acts in an upwards direction opposing the weight force. The magnitude of air resistance dependent on the surface area, velocity, shape, and viscosity of the oil droplet. Viscosity has a proportional relationship with drag force, meaning that an increase in viscosity equals an increase in the magnitude of drag. But if finding the electron was as easy as watching oil fall, we'd all be Nobel Prize winners. Millikan first needed to suspend the electron by alternating the voltage of the plates. As the voltage across the plates increases, a stronger uniform electric field forms, applying an electrostatic force of repulsion to the negatively charged droplets from the bottom negative plate.
This allowed oil droplets to accumulate electric potential energy whilst falling to the bottom plate due to them having light charges. EPE transforms into kinetic energy, a consequence of the electrostatic force of repulsion applied by the parallel plates. Continually increasing the voltage until the electric field's force is greater than the weight force will allow droplets to move upward and vice versa. To suspend the droplets, Millikan adjusted the voltage to a specific value so that the electric and the weight force was at equilibrium, allowing the droplets to float midair.
This was perfect for Millikan, as it allowed him to equate the two forces together. The electric field's force was found by multiplying the strength of the electric field E equals V over D by the charge of the oil droplet. Rearranging the formula, we get Q equals to dma over V. But the mass of the oil droplet was still unknown. By using m equals Vp, where V is the volume of a sphere and P is the uniform density of oil, Millikan could discern the mass of the droplet. Through a crosshair attached to the microscope, Millikan roughly estimated the droplet's radius, additionally using Stokes' law to further validate the radius. Since the amount of electrons in a particular oil droplet varied, Millikan had to record the results of 175 droplets before the charge of a single electron could be found.
Previously, Millikan still had no clue whether the charge of the electron was discrete or continuous. If a pattern could be found between the charges of each oil drop, then the charge of an individual electron would be quantifiable and discrete. Think about it like people. You can't have 2.5 men, only whole number amounts. In contrast, if no discernible pattern could be found, then the charge of an electron would be continuous, meaning that the value could be in between integers.
After almost a decade, finally, a pattern had been found concerning the highest common factor of all the oil droplets. This meant that not only had the charge of the electron been found, but also its discrete quality was revealed. Now, for the big reveal. Drumroll please. The charge of an electron is negative 1.592 times 10 to the power of negative 19 coulombs? Oh, Well, it was the 1900s. What did you expect? At least the charge of the electron we found was less than 1% off the scientifically accepted value. Something you probably couldn't do.